Okay, so you just tried this problem on your own, and we're going to go over it together so you can self-check your work and see how you did. We're starting off with the cosine of x plus the sine of x times tangent of x, and we want to show that that more complicated side that we listed on step 1 is in fact equal to the secant of x, which is what we end up with at the bottom, the simpler side. And if that's true, if this is a chain of logically reasoned steps linked together, then that means that this is a trig identity, this statement at the top, and that those expressions are interchangeable with one another. So in step 1, that's always given. Right, we took that from the more complicated side in the problem. And now to get from line 1 to line 2, we want to look back at line 1 and see what has changed and what hasn't. So the cosine of x plus sine of x, that's the same, right, from line 1 to line 2. Nothing has changed there. So what's different is this tangent of x in line 1 has been rewritten as the sine of x divided by the cosine of x. And that quotient, if we look at our trig identity hexagon, we should be able to see where that comes from. So we've got tangent, sine, cosine, then the reciprocals, secant, cosecant, cotangent. Put the one in the middle to set up our identity hexagon. And if you recall, the quotient is two consecutive vertices, either clockwise or counterclockwise, will give you the quotient of the next vertex. So if we start at tangent here, tangent, if we go counterclockwise around the circle, that would be tangent is equal to secant divided by cosecant. If we go clockwise around the circle, tangent is equal to sine divided by cosine. And that's what we have here. Tangent is equal to sine divided by cosine. So that reason would be a quotient identity. Okay, then our reason for line 3 will be how we get from lines 2 to 3 in the proof. The cosines, when we compare, cosine of x has stayed the same, but now we have, instead of a sine of x times a fraction, sine over cosine, we have just one fraction, the sine squared of x over cosine. So what happened to get from line 2 to line 3 is that the sine x got multiplied times the sine x in the numerator of the fraction, and so that is multiply fractions. Okay, so we're all ready to line 4 in our 2-column proof, and the cosine of x is still here, cosine of x. They just put it over 1 to show that it can be written as a fraction. This sine squared x over cosine of x, this is over here, right? So if we look closely here, I'll put a box around the sine squared of x over cosine of x. That hasn't changed, right? From line 3 to line 4, that's exactly the same. So what's different is this cosine of x got put over 1 to make it into a fraction, and then the person multiplied that fraction by cosine of x over cosine of x, which it doesn't change the value because remember, a number divided by itself is 1, and multiplying by 1 gives you the same thing that you started with. So the value hasn't changed, but what was the purpose in doing that? And if you look down at your next line in line 5, you'll see now by doing that bridge step there, multiplying by cosine over cosine, we end up with two fractions with a common denominator that we can add together. And so that was what was happening in line 4, was that the person was getting a least common denominator. So we'll write finding the LCD, and that LCD was cosine of x. Okay, so then from line 4 to line 5, this cosine of x times cosine of x divided by cosine of x, that just got combined into cosine squared of x over cosine of x. That was multiplying fractions again. And then from line 5 to line 6, now that there is a common denominator of cosine of x, we can combine those numerators to get cosine of x squared plus sine, or cosine squared x plus sine squared x. So that was adding the fractions. All right, now there's a big change from line 6 to line 7. This cosine squared x plus sine squared x got replaced with a 1. Notice the denominator of cosine is still the same for both, so that would be a Pythagorean identity. If you remember our triangles in the hexagon, there are 3 of them that remind us of the Pythagorean identities. So 1 plus cotangent squared equals cosecant squared. That's a Pythagorean identity. Tangent squared plus 1 equals secant squared. That's another Pythagorean identity. And then the one that we're going to refer to is that sine squared plus cosine squared equals 1. That's another Pythagorean identity. And since addition is commutative, sine squared x plus cosine squared x, that's exactly the same value as cosine squared x plus sine squared x. So they're both going to be equal to 1, and we can list Pythagorean identity as our reason for step 7. Okay, now to get from step 7 to step 8, the 1 over cosine has changed to the secant of x, and when we look at our identity hexagon, here's secant, and directly diagonal from it is the cosine. Those are reciprocals. So cosine is equal to 1 over secant, and secant is equal to 1 over cosine because of that reciprocal identity. So that will be our last reason, reciprocal identity. And then we have the secant of x, which is what we started out to get at the end there, which means we can check that off as a verified identity. Okay, hope that helps.